In this set of notes, we're going to talk about energy diagrams, which is a graphical representation of the energy stored and exchanged between certain chemical pathways. And some of the labs that we've done have kind of very clearly indicated that some reactions produce a lot of energy, some reactions absorb energy and end up being a lot colder to their surroundings. And so this is one way for us to visualize where the energy is coming and where the energy is going, and also determine how much energy was required for a reaction to proceed and how much energy was produced as a result of the exchange of the reaction. So there's a couple of terms down the left side of this notes page that we're going to identify, and then we're going to figure out where those line up on this particular type of graph, which we refer to as an energy diagram. And so we've got two different examples. We've got an endothermic diagram and an exothermic diagram. We'll see that the difference there is that the endothermic starts lower and ends a little bit higher, and the exothermic starts higher and ends a little bit lower. And so we're going to talk a little bit about the specifics and where these numbers kind of line up. So you'll be given either a blank graph and have to sketch the pathway, or you'll be given the pathway and have to identify the information presented. So the first term that we're going to talk about is something called activation energy. And activation energy is the energy required for a chemical reaction to occur. So it's hopefully obvious at this point that not all chemical reactions just occur on their own. So something like the combustion of gasoline doesn't happen spontaneously. It doesn't just automatically occur. You have to turn the key in the ignition of your car, and then the spark plug ignites and combusts the gasoline, and then the reaction takes place. So there's something that might require a reaction to be activated. And so this activation energy is simply the energy required to get really to the top of this hill. So when we talk about the reaction pathway, this is kind of like the beginning. So if you think about this as time, this is like time zero, and this is when the reaction is done. So at the very beginning, the reactants, what we put into the chemical reaction, have a certain amount of energy stored within them, but no chemical change to the energy of their stored bonds is really going to occur until they reach the top of this hill, until a certain amount of energy is added to that point. So when we talk about the increase in energy from like this point up to here, if we label this as A, our activation energy here, A is always the energy required to get to the top of that peak, or that what we call an activated complex. So the next two are pretty straightforward: energy of products and energy of reactants. It's the energy stored in the bonds of the products or the energy stored in the bonds of the reactants. So we got energy stored in bonds of products and energy stored in bonds of reactants. So if we label this as B and we label this as C, we would say that at the end of the chemical reaction, this bar where we've got our products, once the reaction's done, we're going to label that as B, where our energy is stored afterwards. And then this bar down here, we're going to label that as C, which is the energy that was stored in the reaction or the reactants at the beginning. So in this chemical reaction, the reactants had 10 kilojoules of energy stored within them. 40 kilojoules of energy were applied, And then a certain chemical reaction occurred once that happened, once we reached the activation energy added. And then the bonds of the elements rearranged and reformed, and the products are now present, but they took some of that added energy and stored it in them, and the energy of the products are now at 20 kilojoules of energy. So that means that there was still some energy that was added that is now not stored in this system, and there's energy that was gained between the two parts, the reactants and the products. So that's really the next term that we're going to talk about, energy released / absorbed, which is oftentimes indicated as a delta H, which is the change in heat energy. So we refer to this as the net energy gained or lost. And the equation, if you want to call it, is pretty simple. It's just your products minus your reactants. Okay, so if we go back to this first energy diagram, we started with the reactants at 10 kilojoules. We ended with the products at 20 kilojoules. So the difference between the two here, if we want to label this as part D, the difference is a positive gain in energy. So if we look at this as the 20 kilojoules of our products minus the 10 kilojoules of our reactants, this particular system throughout its chemical process gained 10 kilojoules of energy stored in the bonds of the products. Okay. And then the last term that we're going to talk about is something called an activated complex. This is the point at which all reactant bonds are broken and no product bonds are formed. So all atoms involved are separate. This is the peak or apex of the diagram. So if we label this as part E on our endothermic energy diagram, this up here, part E, would be our activated complex. Okay, so the last thing I want to talk about before we move on to looking at the next exothermic energy diagram is this term endothermic. Endo means to enter. And so if the reactants had 10 kilojoules and ended with products that gained energy, well, that energy entered into the formula of the products, the bonds of the products, and is now stored in there. So if the system took energy from its surroundings, that means the surroundings, like outside the beaker where this reaction is taking place, technically lost energy. So if your hands lose energy, they feel colder. And so endothermic chemical reactions will always feel cold to the touch because the energy from the surroundings has entered into the bonds of the products. If we think about the opposite to that process, we've got an exothermic diagram where our reactants start with more energy and the products have less energy. And so that energy is then lost to the surroundings or outside the beaker. And so exothermic diagrams will always feel hot or warm to the touch. So let's go through and still label all these parts, A, B, C, and D. So if we start with part A, our activation energy, our reactants have 20 kilojoules stored. They only require the addition of 30 kilojoules to reach the activated complex. We've got the energy of our products down here, part B, the energy of our reactants over here, part C. The energy here, released or absorbed, is actually energy released. And so the difference between the two is now a loss of energy. So this is part D down here. And if we take the energy of our products, 10, minus the energy of our reactants, 20, this is now equal to negative 10 kilojoules. So that negative sign is kind of like a loss or a negative subtraction in your bank account. -10 means that the energy is now lost to the surroundings, and then the energy is picked up by some other source, which is why exothermic reactions always feel warm. And then the last one, the activated complex here, part E, again, the apex, the peak. Once we've hit 50 total kilojoules of energy, the reaction will proceed. And then for this particular reaction, the products, based on the formulas that they form, has a smaller energy stored within it. And therefore, again, energy is lost to the surroundings. Okay, the last little tweak to these energy diagrams is whenever we have something called a catalyst involved. You're probably familiar with that term from last year in biology. They talk a lot about enzymes being catalysts for certain biological pathways. And a catalyst does just that. Like an enzyme, it speeds up a biological reaction. A catalyst increases the speed or the rate, but it's really important that it's speeding up the chemical reaction without actually being used up during the reaction. So a catalyst is just there to make the reaction proceed quicker. It's not actually a chemical reactant. It's not in there. It's not adding any, atoms or electrons or anything like that. It's just there to make the reaction occur faster, and then it can actually be filtered out and reused for other chemical reactions because it's not chemically consumed. The way that it increases the speed is that it lowers the activation energy. Okay, so we can see here in this diagram, we've got the energy of our reactants, the activation energy up here with our activated complex, the products over here. So we've got this original solid line, which is the traditional reaction. And then once a catalyst is added to this chemical process, the only thing that really changes is the height of that hill that the reaction has to climb. So this activation energy requirement is actually this dotted line, and it's a much smaller requirement. The catalyst does not change the energy stored in the bonds of the chemical reactants. It does not change the energy stored in the bonds of the products. So just an activation energy lowering, which means less energy has to be applied to get to the top of this hill or this apex for the reaction to proceed. So what type of a reaction would this actually be? If our reactants have less energy than our products, or we put in a large amount of energy and then our products have a greater amount than our reactants, meaning there's energy stored, that means energy entered. Hopefully that's enough clues for you to also realize that this has the same shape and the same pattern as this reaction diagram up here, which means that this is also an endothermic energy diagram. Okay, so it's just an endothermic energy diagram, also with what would happen if a catalyst was added. For this exothermic diagram, if we threw a catalyst in there, same process, except we put in some kind of a dashed line to indicate that the required amount of energy is less than what it was before the catalyst was added.